Alright, so what we're going to go over today is Manual S. We're going to go over the quick and easy way to determine whether or not the equipment you selected will meet Manual S. And Manual S is pretty simple in and of itself anyway. There are a lot of other things that you can take into account and that Manual S can teach you, but if you're just trying to select equipment, these are really all the rules you need to know. Okay. Um, First thing is you have to have already done a load calculation. You need to know the total heat required for the house based on design temperatures, the total amount of cooling, sensible cooling based on design temperatures, and the total amount of latent cooling needed based on design temperatures. Once you have that, you can go into selecting equipment. Um, so with that in mind, let's talk about the rules that you'll have to follow. So this is my little cheat sheet on Manual S. You can find a couple others like this online, but this is just one page, all the stuff you need to remember, done. All right, and it's all pretty simple. All right, so the most important thing is how much you can oversize equipment, right? Because you should never undersize equipment unless you discussed it with the homeowner and they understand that the cooling performance and the heating performance may not quite get to the design temperatures on load days, right? So, for our area, for Virginia, Fairfax, Virginia, um, your design days are 95 degrees outside. You should be able to maintain at least 75 degrees inside. At 17 degrees outside in heating, you should be able to maintain at least 70 degrees inside, right? And cooling, we were trying to maintain 50% humidity generally, right? So if you undersize equipment on a 95-degree day, you may only be able to get the house to 76. Odds are, you're still going to be able to maintain close to that, but, on a 100-degree day, for instance, you might only be able to get the house to 77, 78, maybe 80, right? So it's not, that's another good thing to keep in mind. Once you hit 95 degrees outside, that equipment should essentially be running all day. So a common complaint you get on a very hot day is my equipment's running all the time and it's not cool in the house. Okay, what's the temperature in the house? It's 74. What do you got it set at? 70. Okay, well, if it's 100 degrees outside, and the equipment can get down to 74, that's pretty good, right? For our area, for what we designed the equipment for. If it's running all day and it's keeping it at 74, that's actually better than what it was designed for. So that would be normal, all right? You can always double check and make sure there's nothing else that would improve the cooling performance, but that would be normal. That would be a good thing, right? Um, but you should never really undersize unless they understand that it's not going to perform as well. The benefit to undersizing is obviously you're going to use less energy because it's smaller equipment, so they're going to have a lower bill the majority of days. Better than undersizing equipment is, really using two-stage equipment or multi-stage equipment. That would be a better option than undersizing it. But if you want to go down, you can go down to 90% of load, but you can't ever go below 90% of load, and that's generally not recommended. Your equipment should be at least 100% of the load, and then you can oversize it based on the type of equipment you're using. So for gas equipment, whoops, fix that. For gas equipment, we can go up to 140% of load, right? So that means that, say, a house's heat loss in the winter is 48,740 BTUs. The heat output of the equipment could be as high as 68,236 BTUs. Um, and an 80,000 BTU 80% furnace would have a BTU rating of 64,000 BTUs. So a house with 48,000 BTU, a 48,740 BTU load, it is perfectly fine to use an 80,000 BTU furnace. A 100,000 BTU furnace would be too big. A 60,000 BTU furnace, actually let's do that math real quick. A 60,000 BTU furnace times 0.8 for 80%er would be 48,000 BTUs. So it would actually be really close, right? A 60,000 BTU furnace would be pretty close, but an 80,000 BTU furnace in this case would probably be better. So that's what you can do. You can do up to 140% of load on any gas equipment. So that's your boilers, furnaces, things of that nature, right? So here's our example. 48,740 times 1.4 equals 68,236. 80,000 times 0.8, and that's assuming an 80% furnace, would be 64,000 BTUs. If it was a 90% furnace, that would be 80,000 times 0.9. 80,000 0.9. 80,000 times 0.9 would be 72,000 BTUs. So a 90% furnace in this case would actually be too big, right? So if we were moving to a 90% furnace, we would actually want to go to, I think, say it came in 60,000 BTUs. Some of them come in 60, some of them come in 70, but 60,000 times 0.9 would actually be 54,000 BTUs. So if you were going 80%, you would want 80,000 BTU furnace, but if you were going 90%, you would want to go down to a 60,000 BTU furnace. And that's not actually that uncommon for the efficiency to change the size of the equipment you're going to want to install. So that's something to keep in mind. So there's gas equipment. Gas equipment's super easy, up to 140% of load. It's really hard to run into a situation where you'll be stuck between numbers or something. And not bad at all. All right, air conditioners. Air conditioners and heat pumps in cooling dependent climates. Now, we are a heating dependent climate here in Fairfax, Virginia, but other areas could be cooling dependent. Florida, I'm pretty sure Florida would be a cooling dependent environment, right? Cooling dependent climate. A little bit farther south and you start to hit cooling dependent climates. But we are a heating dependent climate, right? Air conditioners and heat pumps in cooling dependent climates are 115% of load. So that's on the total BTUs of the equipment. So our sensible and our latent together. All right. So if the total heat gain of a house, sensible and latent, was 23,440 BTUs, the cooling output of the air conditioner could be up to 26,956 BTUs. So 23,440 times 1.15 is 26,956. Now for now, I just want you to remember that half of excess latent load can be added to sensible load to meet load requirements. We'll talk about that in a bit, but for now just keep that in the back of your head. That note's there just so you have that note, because that 26,956 BTU air conditioner, right? Whatever air conditioner you pick needs to be able to meet the sensible and the latent load requirements independently. So we'll talk about it when we get to the heat pump example, because down at the bottom I've got those things mapped out separately, or when we get to sensible heat ratio, we'll talk about that. That way we can throw a couple numbers out there, but just understand that if your latent load, if you have more latent capacity than you need, half of what's left can be added to meet your sensible if the sensible load of the equipment's not enough. All right. So that note's just there so I could put it somewhere on the sheet. There's no other real good place to add it in there. So I just added it under air conditioners just so you'd have that note if you ever needed it. All right, heat pumps in a heating dependent climate, you can do up to 125% of the cooling load. So when we're talking about oversizing air conditioners, what's the problem with oversizing them too much? Well, the problem with oversizing them too much is you can end up with high humidity in the home because the equipment's short cycling. So if you start going way too much over the load requirement of the equipment, your equipment's going to short cycle more, especially on mild days, and you're not going to be able to maintain lower humidity levels. Of course, we're assuming single stage standard equipment here, right? We're not talking about variable speed equipment that can control the humidity in the house using sequences where it lowers the fan speed at the beginning of operation and so on and so forth. If you're putting in, single stage standard equipment, 14, 16C or something like that, then if you oversize it, you could end up with high humidity in the house, again, especially on mild, humid days. So we don't want to oversize it too much. But heat pumps, right? Heat pumps are actually a situation where we kind of want to oversize, because as we oversize the heat pump, we get more heat output on colder days and therefore save energy on those colder days. So that's why it matters whether we're in a heating or a cooling dependent climate, because we're not really too worried about oversizing that heat pump if most days are cooling days anyway. But in a heating dependent climate, we do want to try and push the envelope a little bit and oversize that equipment so that we can save energy for those times we are heating. So, you get up to 125% of the load on that, and you probably want to shoot for somewhere close to that most of the time. It's not necessary, but it will, in general, save more money, that energy you save in heating as opposed to the energy you save in cooling. And the dangers of oversizing are slightly overstated here and there. It's going to be hard for you really to get to the point where you're short cycling so bad you don't get any latent heat removal, especially if you set fan speed to deal with latent heat more if you need to. Um, in general, I know we say 400 CFM per ton, but really you want to shoot closer to 350 to 375 CFM per ton for our area anyway. Most equipment these days kind of gets set up for closer to 350 CFM out of the box. So, we can usually mitigate the downsides of the oversize pretty good and still get better heating performance with a heat pump. So it's just something to keep in mind, something to think about. Especially when you get to variable speed heat pumps, you want to oversize it usually about a half a size to a full size, right? So if you're putting in a variable speed heat pump and the house is 2.5 ton, you really want to go to a 3-ton variable speed heat pump so that you get that extra heating performance on colder days, and they run that heat pump a lot less. And obviously, since it's variable speed, the oversize on the air conditioning side of it is irrelevant anyway. So here's our example here. If the total heat gain of a house is 27,640 BTUs, the cooling output of the air conditioner, the heat pump, I should fix that now. Let me fix that before I upload it. The cooling output of the heat pump can be up to 34,550 BTUs. 27,640 times 1.25 equals 34,550 BTUs. So let me save this before I forget. There we go. All right. Let's see if I can lock that. All right. Electric heat. So electric heat is pretty simple. You size it as close as you can, as close as to 100% of the load as possible without going under. there's really no reason to undersize electric heat, and you're usually going to be in increments of 2.5, 3, or 5 kW. So whatever meets the load, okay? So, I didn't put an well, let's go through this and then I'll probably put another example here real quick. All right, so it's very difficult to oversize electric heat, like I just said. The best practice with it is to make an effort to stage the electric heat based on outdoor temperature. So, for instance, if a house has a heating load of 60,000 BTUs and the heat pump can put out 37,000 BTUs at 47 degrees outside, then you might only want to let the first stage run until it gets colder outside. So once it gets below 47 degrees, then you allow the second stage to come on. Now that requires you to have outdoor thermostats that are wired to the electric heat to lock out stages based on outdoor temperature. But if you do that, your equipment will run longer. It'll be a more even heat in the house. It'll be more comfortable, and you'll get better performance and more energy savings, right? But it doesn't get done a lot these days. I've met a couple guys where this is what they really like to do, but I've serviced a lot of houses. I haven't seen many with outdoor thermostats to lock out electric heat stages. But that is a good upsell that you can do on an install, and it has benefits. Maybe not as many benefits as moving up to a variable speed equipment, but there are benefits there. So it's just something to think about. But there are fewer repercussions to oversizing electric heat. It's pretty hard to put yourself in a situation where you way oversize the electric heat. In general, you should err on the side of putting an extra 5 kW in there. It's not it's not hard to just delete a strip of electric heat if you need to. So the biggest, and I didn't note this here, but the biggest factor that's going to limit how big of an electric heat kit you can put in is going to be the size of the wire going to the kit, right? The wire can only handle so many amps. Don't let the wire overheat because you oversize the heat kit. But other than that, other than short cycling, you're not going to run into any problems oversizing electric heat most of the time. Oversizing gas equipment, can start to get pretty dangerous. If you're short cycling and you're overheating the heat exchanger and stuff like that, you're going to it's going to break down more often. It's going to be more likely to fail. But with electric heat, most of those problems you don't have. It's just a matter of having enough heat without going completely overboard, right? So remember, BTU output of electric heat is 3,414 per kW. So either 3.414 times every watt or 3,414 BTUs per kW. All right. So every 5 kW is about 17,070 BTUs. So 5 kW times 3414 equals 17,070 BTUs. So you can basically, if you want to shortcut it and just say 5 kW is 17,000 BTUs, every 5 kW I have in there. So, 10 kW is going to be 34,000 BTUs basically, and so on and so forth. So if we go back to our first example real quick, right? We go back to our first example of our gas equipment where the load was 48,740 BTUs. We can figure out how many BTUs we need. All right. We can figure out how many BTUs we need, how many kW we need by going 48,740, all right, divided by 3414, and we will get that we need 14.27 kW. So that would be a 15 kW heat kit, right? So an 80,000 BTU furnace is equivalent to a 15 kW heat kit, basically. In this instance, anyway. It's actually 64,000 BTUs, you could almost be 20 kW. 80,000 BTU furnace can really put out about 20 kW worth of heat, right? But it's close. Yeah. All right, so that is electric heat. All right, now it starts to get a little bit more complicated when we're talking about target CFM and sensible heat ratio. So the next question you have to ask is, okay, I know how many BTUs I need for the house. How many CFM do I need for the house, right? It's not as easy as saying I need 400 CFM per ton. You know, this heat pump up here that we need 27,640 BTUs or 34,550. This 34,550 that we can be up to does not mean that we use a 3 ton at 1,200 BTUs. That's not necessarily the case, okay? It's not necessarily the case that it's going to be 400 CFM per ton. Remember, our range is 350 to 450 CFM per ton, and maybe even more, based on every ton of equipment. So how do we determine if we want 350 CFM per ton, or we want 450 CFM per ton, or 500 CFM per ton, or whatever? Well, we do that by determining the sensible heat ratio. The sensible heat ratio gives us an idea of how much of the load is sensible and how much of the load is latent. So that makes a big difference, because the more latent heat we have, right, the lower we want the airspeed to be so that we can remove more humidity. Remember, latent load in the case of cooling is basically just humidity load. All right? So, to determine how much CFM we actually want, we have to determine that sensible heat ratio, take that into account, and use some rules that Manual S gives us to determine what we want our delta T to be. And once we know what we want our delta T to be, we can use that to calculate how many CFM we need. All right? So there's some math involved, but it's not that bad. If you just keep it simple in your head and follow the steps, it's pretty easy. As long as you have the sensible load of the house and the latent load of the house, you should know how many CFM you need in the house after you run a couple numbers. All right? It's easy as that. It doesn't matter how big the house is or how many windows you have or whatever. You've already got the load calc. Tells you what the sensible load is, tells you what the latent load is. We know what our target CFM should be. So, sensible heat ratio is used to determine what delta T we want in cooling. The desired delta T allows us to determine our desired CFM. The lower sensible heat ratio, the lower the delta T. Lower delta T removes... I messed that up. We gotta fix that. The lower the sensible heat ratio, the higher the delta T. I originally wrote this the other way, but I felt it was better if I put it on this. So let me fix this, and then we'll repeat this sentence. And I ain't editing this out. It is what it is. All right. So the lower the sensible heat ratio, the more latent heat we have, the higher the delta T. Higher delta T removes more humidity because it will generally result in the air moving slower across a colder coil. All right. So our sensible heat ratio equals our sensible heat gain BTUs divided by our total heat gain BTUs. So our cooling load, our sensible cooling load divided by our total cooling load. All right. For example, if we have a house with a sensible load of 24,520 BTUs and a latent load of 2,940 BTUs, the total load is 24,520 plus 2,940 equals 27,460. So our sensible heat ratio would be that 24,520 sensible load, right, divided by the 27,460 total load, and that would equal a 0.89 sensible heat ratio. So at 0.89 is a high sensible heat ratio, okay? That means we don't have much latent load, right? We only have 2,940 BTUs of latent load, but we have 24,000 BTUs of cooling load. So the sensible load. So the sensible load is almost 10 times our latent load. So that's a pretty high sensible heat ratio. That means we're probably in an area that's not very humid, or we have a house that's, sealed very well, but has a large amount of windows or something, right? So in other words, there's a pretty high heat gain for the size of the house, but not much of it is latent, mainly because most of our latent load comes from infiltration. Okay, most of our latent load comes from infiltration from outside air to the inside, and that brings in the humidity from the outside, which adds to our latent load. People don't add that much latent load. It's like 200 BTUs per person or something. So most of that comes from the outside because there's nothing else that adds latent load except for people and outside air. If you go back to your load calcs, you'll see that. So based on our sensible heat ratio, we can determine our desired delta T. All right. So our desired delta T, if our sensible heat ratio is below 0.8, then we want a 21 degree delta T. So this would mean that at least 20%, right? At least 20% of our load is latent, and then the other 80% is sensible. So 20% or 21% or 30% for that matter is a pretty high latent load. So we want a higher delta T to remove that latent load. And this is here to cheat later. This 1.08 times these numbers is there to just get a cheat number later. So you have it. We'll talk about that shortly. Sensible heat ratio of 0.8 to 0.85 is a 19 degree delta T. So this is kind of average. This is pretty close. So we usually want a 20 degree delta, right? 20 degree delta is what we always say we want on a split on an air conditioner, which is wrong. We don't always want a 20 degree delta. But that's pretty close, right? And look, that's pretty close because our sensible heat ratio is usually somewhere between 0.8 and 0.85. We're right in that range. So if we're in this range, a 19 to 21 degree delta T, a 20 degree delta T usually does a pretty good job of handling humidity and sensible load. That's not always the case, though. It's not always the case that a 20 degree delta T or so is correct. But in the majority of cases, it's a pretty safe bet. But that's not how we figure out what it should be. All right. And then finally, an SHR above 0.85, which is a pretty low latent load, right, is a 17 degree delta T, which is what we had up here. We had a 0.89 sensible heat ratio, so that means we would want a 17 degree delta on this equipment. That's uncommon, right? But it's possible that's what you want. So now that we know this, if we know our sensible heat ratio and we know our desired delta T based on that sensible heat ratio, now we can determine how much air we want through the equipment and cooling. So for heating, for determining CFM and heating, it's pretty simple. You go by the manufacturer's recommendations on the furnace or whatever, right? Or if you're using a boiler, obviously you're not even dealing with CFM. But when it comes to a gas furnace, you want to kind of pick a CFM that's a nice happy medium that keeps you in the heat rise that's required for the furnace. So if you want to know target CFM for heating, basically pick a number based on the furnace you pick, usually somewhere around 40 to 50 degree delta T, right? On a piece of cooling equipment, we determine it using the sensible heat ratio, and we determine target CFM using the following formula. CFM equals sensible BTUs divided by 1.08 times delta T, which is why I have these cheat numbers up here, right? 1.808 times each of our standard numbers that we would pick. But if you have seen a heat rise formula for calculating CFM, so that you can use your furnace to determine, you can use your heat rise through your furnace or your electric heat to determine how much CFM the system is putting out, then this formula should look very familiar, because all we got to do is take out sensible, and we're talking about BTUs divided by 1.08. A lot of times I write it as output BTUs divided by 1.08 times delta T, and that's our heat rise formula. It's the exact same formula, but this is what we use to determine what CFM we want in cooling. Okay, so the fact that we have to use sensible BTUs is important, but these should always give you CFM. This is your equation for determining CFM based on BTUs and delta. So, for instance, CFM of 24,520, right? Same one we used up here, divided by 1.08 times 17. 1.08 times 17 is 18.36. So 24,520 divided by 18.36 gives us 1335 CFM. So equipment that has a sensible load of 24,000 BTUs in a place probably like Arizona or something is what this would be 1,335 CFM. It's a lot, right? That's a pretty big CFM number. We should try and select equipment using this target airflow in cooling with a range of plus or minus 10%. So a lot of times you're not going to find published data for 1335 CFM, but you pick the published data that's as close as possible to this number while trying to be within plus or minus 10% of it. And that's how you determine how much CFM you need. So this right here should already tell you we're probably in the 3-ton range. We need under 30,000 BTUs, but we're in the 3-ton range on equipment. So this is why it's important to know manual S, because the load isn't what you think it is. The equipment doesn't put out what you think it does. And there are many things that can factor into what the actual BTU output of a piece of equipment is, and so on and so forth. So if you understand these rules and have done a few load calcs, you'll start to see that 3-ton ain't 3-ton, and where you want this changes a lot. So it's interesting once you get to know it. It's hard to do it until you've done a few real life examples. It's hard to really picture what I'm talking about. But if you ever get the chance to do a couple real life load calcs, even on something as simple as an addition or something like that, and pick equipment based on this criteria, you'll see that A, that a lot of stuff is oversized, and B, that equipment doesn't necessarily put out the BTUs you think it should put out. Okay. Now, before I move on, let's talk about that excess latent thing again. So, if we were trying to select a heat pump, right, we need 27,640 BTUs total. Alright, say we found a piece of equipment that did, let's just make up some numbers here real quick. Matter of fact, I'll do another, can I do another text box? You know what, let's just, here. Let's just do another text box real quick. Let's say we find some equipment. We're just going to make up some numbers for now. We're going to look at actual equipment data in a second, but making up some numbers. Let's say we found some equipment and it puts out 23,000 sensible BTUs, and it puts out 6,000 latent BTUs. So we found a piece of equipment. Let's pretend it's a 2.5 ton piece of equipment actually that we found, and these were the BTUs it puts out. Alright, well, the problem is, even though this is within our target range, we're not oversized more than 25%. We've got enough total. We've got 29,000 BTUs total, right? So we beat our total number. We're less than 15% oversized. But the problem is that our sensible capacity doesn't meet our sensible requirement, because our sensible requirement is 24,520 BTUs, right? As a matter of fact, let's change this real quick. Let's make this 7,000 so I know this math will work, because I'm starting to think this math's not going to work out. Alright, so we found a piece of equipment. It's 23,000 sensible, 7,000 latent, 30,000 total. Alright? Our sensible is not enough to meet the 24,000 BTUs we have sensible. So what we can do is okay, we can say, alright, so the sensible is not enough, but out of the 7,000 latent BTUs, we only need 2,940 of it. I think it would have worked out, but anyway, we only need 2,940. So that equals That equals 7,000. Let me clear this real quick. 7,000 minus 2,940 equals 4,060. So out of that 7,000 BTUs, we really only need 4,060 of them in latent. Okay? We only, out of that 7,000 BTUs, we only need 2,940 of them in latent. So we have 4,060 latent BTUs left over that we can use to determine our sensible load. The problem is we can't use all of it because ACCO won't let us. And really, that BTUs are geared towards latent removal. They're not geared towards sensible removal, right? Because we're not really, it's really latent BTUs, it's not sensible. But what we can do is we can take that 4,060 that we have left over, divide it by 2, okay? And that'll give us 2,030. That 2,030, that half of the excess latent, is what we can add to our sensible, right? So we can add that 2,030 to our sensible. So that our new sensible total, what the heck just happened? I must have accidentally deleted something. Alright, let's put that back up there. I gotta put it all back. 4,060. Out of that 4,060, we divide that by 2. That gives us 2,030. So we can add that 2,030 to our sensible. Alright. And that means that our actual sensible capacity per manual S would be 25,030. So now this 25,030, okay, is bigger than the 24,520. If that didn't make sense, just remember half of excess latent can be added to sensible, And if you're in a pinch where it seems like none of your equipment works, come back and watch this until you get it, and use that to your advantage, because there are times where you're kind of in these in-between loads and it seems like nothing is going to work. But if you remember that you can add half of excess latent to your total, you'll get there. All right, so that's your example for that. Just try to keep that in mind. Other than that, it's not that important. It's semi-rare that you actually have to take that rule into account. But just remember that you're sensible and you're latent. The equipment has to be able to meet those numbers independently. If the total's right, it doesn't mean that the equipment is properly sized. The equipment has to be properly sized and have enough sensible and latent heat available to work. Okay? And that is most of what Manual S is about. That is the most important points out of Manual S, to make sure that you're not oversizing or undersizing equipment. So, with that in mind, let's take these numbers we had down here, okay, for this target airflow and our load, right? Our load right here. Let's take these numbers into account and look at some actual product data. We are going to look at some Goodman product data and find some equipment that's going to work with this load we had down here. Okay? So, first off, where do you get product data? Well, it should be pretty easy. It's not that hard, especially these days with Google. It's not very hard. What you used to have is a big book with all the product data for the equipment manufacturer in it. Now we can find it online pretty easy. So, if we go to Goodman's website, here's Goodman's website back here. If we look up their product data or look at their literature library, we can go down, find heat pumps, and then go into GSZ 14. Let's look at that one. Pretty sure that's what I was on anyway, right? Let me make sure. I might have been on a 16. Let me check that real quick. Yeah, no. GSZ 14 is what we're going to look at. So, you pull up a GSZ 14, and it's going to give you all the stuff on this equipment. And what you're looking for is product data, expanded product data, or engineering manuals. You find one of those things, one of those documents, name that for your equipment, and it's going to give you all this information about the equipment, all the stuff you should need concerning that equipment. And then after you get past amperage and sizes and suction line sizes and all that, you'll get into expanded cooling data. And you have all these pages of expanded cooling data for every size from a 1.5 ton to a 5 ton with their air handlers, right? And with air conditioners, it'll be with all their coils, right? So, if you need it with a coil, you might have to ask them for their expanded product data with a coil, right? You need to match the air conditioner to a coil and get all the product data. And then if you keep going, most manufacturers, if you just keep going, you'll get to their heating data, and their heating data will be on usually something looking a little different, but it could look relatively the same as the cooling data. Alright, so you just need to find this information and then look at the product data. And let's switch back real quick. What I picked out was this product data. Alright, the yellow highlights right here in the middle, that is from Goodman. The other highlights on here are from me. Okay, I highlighted this stuff because we're going to talk about it. Now, before we talk about it, One more important note, and let me switch back to the web browser real quick. One important note is if you're looking at this product data, you're usually going to have a couple things, and this is how Goodman points it out. You're going to have these indoor dry bulb temperatures and these outdoor temperatures, right? And then with Goodman, they've got this at 67 degrees wet bulb, right? And then they have this one, which is at 63 degrees wet bulb. This one is 80 degrees outside. This one is 75 degrees outside. So they've highlighted this here, and then they've highlighted this here. For most equipment, all the numbers are at AHRI rating conditions. So this is how they determine the efficiency of the equipment. 80 degrees inside, 67 degrees wet bulb, so that's 80 degrees at 50% humidity, and at 95 degrees outside. These are how they determine the efficiency of the equipment. These are not what you use for your load calculation. If we look at this one, it says the shaded area reflects ACA conditions. So at 75 degrees inside, we're always 75 degrees inside for cooling, right? 63 degrees wet bulb, that's 50% humidity. So at 50% humidity, 75 degrees inside, at 50% humidity inside, and then it says 95 degrees outside. Now the 95 degrees actually depends on where you live. You might design for 85 degrees outside where you live. You might design for 105 degrees outside where you live. But in general, a lot of places are going to be at 95 degrees. So I guess that's why they picked that shaded area. So these are ACA conditions, and that's what we want. We want ACA conditions, not AHRI conditions. AHRI conditions tell us squat. Okay, nothing. They don't matter. All that's for is rating the efficiency of the equipment. What we want is ACA conditions. So let me switch back to where I printed this one page out of there on Bluebeam so we can look at some notes. So again, when you're picking your equipment, especially in Fairfax, Virginia, right? But this could change a little bit where you live, but a lot of these numbers stay the same. One of these numbers that stays the same is the 75 degrees inside. You always pick your cooling equipment at 75 degrees inside. The other thing that should probably never change, it can if you want to design at different humidities, but in general you design at 50% humidity, so it should be a 63 degree wet bulb inside. Alright, so now we know we're in this set of rows, right? And we are in this set of columns if our outdoor design temperature is 95. If you have a different outdoor design temperature, you should be in these other columns, right? But in general, you're going to be, especially Virginia, you're going to be at 95 degrees, so you're at this set of columns, right? And really, we can narrow that set of columns down to this 63 degree wet bulb. So now we're right here, right in line with the ACA design conditions. Now, we have to narrow these rows down. Well, to narrow these rows down, most cooling equipment, it's going to give you 3 options on airflow. This is kind of like your low airflow, your medium airflow, and your high airflow sides. Okay, so you pick the one that's closest to your target airflow. Our target airflow was 1335 CFM. So we're going to pick the airflow at 1350 for now. Right, so we're going to be in this bottom one. Now, 1200 CFM is still within 10%, right? That's still within 10% of our target. So we could go 1200 CFM, but for the purposes of this example, we're going to pick the one that's closest and go with 1350. All right, so now we are in this row. and this column. So we are right here. This this right here is where we're gonna pick our equipment. So the numbers they give us right here are MBH. So this is thousands of BTUs. This is how many thousand BTUs this equipment puts out. All right. This is our S divided by T. So this is our sensible divided by total. And this is actually at 0.77 sensible heat ratio. So that means 77% of this 33,700 is sensible, and 23% of this is latent. So we'll do that math shortly. But this is how Goodman does it. This is one thing that changes from manufacturer to manufacturer, how they present total versus latent load. But in Goodman's case, they give you the sensible divided by the total. So they basically give you the sensible heat ratio, and that's what gives you how many BTUs of each you have. They give us the delta T that you're going to have, and this is a 19 degree delta T, which actually, if you go back to the cheat sheet, is too high, right? That's a 19 degree delta, and we want a 17. But once we're done picking it, you'll see that it still works out. And then they give you a bunch of other data that's basically irrelevant, and as far as Goodman goes, the kW, the amps, yada yada, we're not too worried about that. Alright, so that 33,700 BTUs, let's go ahead and put that down. So this equipment at our design conditions does 33,700 BTUs. So if we were picking a heat pump that is less than the 34,550, so we would be okay. I used the same numbers for the example for the heat pump. So if we were picking a heat pump, this would actually be fine. We're pushing it, okay, but it would be fine. So we can go ahead and say, okay, yeah, it's 33,700 BTUs total. All right, so that means 77% of that is sensible, right? That's what they're telling us here. So if we do 33,700 times 0.77, that means 25,949 is sensible. So if we subtract that from the total, we'll find out how much we got latent. So again, it was 33,700 total. Now we know that 25,949 of that was sensible. So we know that the latent load has to be, or the latent capacity rather, has to be 7,751. Alright, so now that we have these numbers at this airflow, we can compare them to the equipment we had, right? So let's just move this over onto our cheat sheet real quick. And we can see that the 25,949 is higher than our 24,520. The 7,751 is higher than the 2,940. The 33,700 is within 25% of our 125% of our total. So this equipment right here would work at these numbers. All of this would work out. We can put this equipment in, set it at about 1300 CFM, and it'll work. And we'll design our duct then at 1300 CFM. And that's everything going through manual S. Now, before we finish this up, let's bring in one more thing. This, oops, let me put this somewhere. No, stop moving the wrong thing. Let me get this thing to behave. Alright, so this is the same equipment, but this is the heating data. Okay, so now we're looking at the heating data for the equipment. So we can see this equipment puts out 32,000 BTUs at 47 degrees. What we need to know, alright, sometimes what we need to know, especially if we're doing mini splits or something where we don't have electric heat, what we need to know is the heating output at our 17 degrees outside. So this 3-ton equipment at 17 degrees outside puts out 19,000 BTUs. If you want to size your electric heat really close, some jurisdictions will allow you to only size your electric heat to make up the difference between what's required and what the heat pump won't do. But that's not really recommended. In general, you size your electric heat to 100% of load, so that's one thing. The other thing is to determine where it drops off. So if you know your load at these different temperatures, which if you're using software, it's not that hard to find, you can determine how many BTUs of electric heat you need at these different temperatures, and again, you would use that to lock out the heat when it's too warm outside to need to use electric heat. The other thing is, like I said, if you're using this as your sole heat source, so you don't have backup heat, then you need to make sure that at your design temperature, so for us that's 17 degrees, you need to make sure at your design temperature you can put out enough heat. And again, I ran into an issue recently where, for whatever reason, using mini split systems, right, variable speed mini split systems, so I wasn't too worried about an oversize. There are downsides to that, right? There's still downsides to oversizing mini splits and variable speed systems, but it's not too big of a deal. As long as you're okay on cooling, you can oversize it to meet your heating load. I ran into a situation where a 3-ton multi-port mini split could not put out enough BTUs to serve a house, right? But what was it? No, is it? Yeah, a 3-ton couldn't do it. But a 2-ton and a 1-ton single unit mini split could handle the load of the entire house. So same manufacturer, same product line, the multi-port outdoor unit wouldn't work, but a 2-ton and a 1-ton indoor would work. That's why you got to look at heating data, because it's not intuitive. It's not, you know what it's going to do. It's not because they say, even if they say this thing puts out the entire heat load at 0 degrees, don't believe them, because it might depend on what you match with it, which pieces of equipment you use. It can make a big difference sometimes. So that's why it's important to know. So, last tip. The last tip I can give you is, if you're replacing equipment, if you want to go that extra mile and you're not doing a load calc, right? Really, if you're replacing equipment, you should always do a load calc. But I know real world, not many people are going to do that. So if you're not going to do that, the only other pro tip I can give you is, if at all possible, look up the original expanded cooling data for the equipment that you're replacing, if it's available. And if that's available, you can try and match the new equipment to the original cooling data. So if you're going equipment that's a higher efficiency, or it's just a different manufacturer because it really changes manufacturer to manufacturer. If you can look up the expanded cooling data for the original equipment, you can compare that to your new equipment and make sure you're doing as good or a little bit better than that. Because it changes over time, right? All these numbers tend to change a little bit over time, and newer equipment's going to put out closer to nominal BTUs, and that's going to affect what you're putting in. Or you might be working on with a manufacturer that has, slightly lower output than you'd expect for a 3-ton unit or something. So you need to verify that you're putting out the same BTUs as you were before, assuming the original equipment worked well. If the original equipment didn't work well, then you should probably be doing a load calc. But if you're trying to avoid a load calc, it's a good extra step to look at the expanded cooling data of the original equipment to try and compare that to what you're putting in to make sure you're giving apples to apples. Is it really that important? No, but it's just an extra step you can take to try and determine that you won't have any issues after you change out the equipment. Because, of course, 90 to 95% of the time, all these things work out pretty well. But that 5% that it doesn't, you want to be the guy that can figure out where it went wrong. And this is just another way you can try to figure out where it went wrong. All right. That's it. That's Manual S. I know some of it's a little confusing. Most of it's really easy. I'd say the only thing that's really complicated about it is that whole half of excess latent thing. But other than that, it's just some hard and fast rules. This is the most you can oversize equipment. Don't oversize it more than that. And that's how you make sure you're compliant with Manual S when you select equipment. And that's all. Have a good evening.